Before we talk about stretches, let's use what we've learned about translations to understand how replacements work. Here, we're going to take y equals x squared, the base form of a parabola, and we're going to shift it to the right and up. Now, at this point, we're probably comfortable with the fact that when we see x minus 3, that moves us to the right. And when we see that plus 2 outside the bracket, that moves the graph up. But it's worth dissecting exactly why that is. When we talk about the parameters of a, which is the coefficient in front of the squared bracket, and h, which is the 3 here in x minus h, so when we say x minus 3, it's actually a positive 3 that is h, and the k value, which here is that plus 2. Two of those parameters, a and k, are affecting the y variable, and the h parameter is affecting the x variable. Well, if the parameter, a and k, is on the opposite side of the equation from the variable it's affecting, then its effect will be direct. So that plus 2 makes the y value increase by 2. However, if we have an h value, such as a 3 here, when we see a minus 3, because we are on the same side of the equation as the variable it's affecting, the effect is opposite. So when we see a minus 3, which would normally make us think moving left 3, it actually moves it to the right. It might help then if rather than looking at this simplified form, we go back one step. If we were performing replacements, in order to shift the graph 3 right, we would replace x with x minus 3. And to move 2 up, we would replace y with y minus 2. That's not a typo. To move y up, we would replace it with y minus 2. So in the first step after the replacement, we see y minus 2 equals x minus 3 squared. And here, the k parameter, which has this effect on y, shows up as minus 2 and actually moves us up 2. And the h parameter shows up as that minus 3 there, moves us right 3. Now we see that though they're both having an opposite effect, at least it's consistent. In this regard, vertical translations are affected the same way as horizontal ones, which is to say, whatever the sign is that you see, you perform the opposite. Once we move that k value over, which is what we're more accustomed to seeing, we create an inconsistency in the logic of the equation. That's not wrong, but that does sometimes make it harder for students to keep these ideas straight in their head. So now, as we talk about reflections, let's still talk about replacements to try and keep that consistent understanding. Let's say we started with the graph of y equals x minus 4 squared. Here we see a parabola moved 4 units to the right. If we wanted to reflect this over the y-axis, we would replace x with negative x. Notice I haven't introduced any special brackets here. I'm just straight up replacing the x with a negative x. If we want to see a simplified form of it, I could factor a negative 1 out of the negative x and negative 4 bracket. Notice that that negative 1 would still be affected by the exponent of 2. And so when we square it, it would become a positive 1. Now, if we wanted to reflect vertically, which is to say over the x-axis, we would replace y with negative y. If we did this, our next step in simplifying will be to multiply both sides through by negative 1. So we can see now that both translations and reflections can be managed using replacements. It's a little bit different in translations where we talked about things happening oppositely to what was expected. With reflections, you were probably expecting that when x was replaced with negative x, it shifted over the y-axis, and when it was y with negative y, it was over the x-axis. But nonetheless, we've shown how the replacement serves us here. Let's connect back to some of our earlier lessons. We now see that when we were talking about vertical reflections over the x-axis as making the entire right side negative, it's really because we had this replacement of y with negative y. Similarly, when we talked about translations up or down, when we saw adding k to the function, or an addition on the right side, it's really because we had introduced y minus k as a replacement for y on the left side. In exploration 1, let's have a look at how stretching can affect a graph. We start with f of x equals the square root of x plus 4 minus 1. So this is a radical function that's been moved 4 units left and 1 unit down. Here we see the vertex at negative 4 and negative 1 as our starting place. We're asked on the same grid to construct a new graph called g of x, and we're going to do so by multiplying all the original y coordinates by 2. So here, the heights that were originally 1 became 2, or negative 1 became negative 2. And the heights that were 2 became 4, and the height of 0 was doubled and remained 0, so that was an invariant 1. What's important to note is points that were below the axis were stretched and became more below the x-axis, and points that were above the x-axis stretched up and became more above the x-axis, and then points on the x-axis did not move. So unlike a translation, which moves all the points in the same direction and in the same amount, here, some points are not altering their position, and some are altering it more drastically than others. So we can say that this is a vertical stretch, and specifically a vertical stretch about the x-axis, because we have to stretch relative to something. What that means is all points are becoming twice as far from the x-axis. We describe this with the mapping rule of xy becoming x and 2y. Remember that because we're stretching relative to the x-axis, it's our initial distance from it that gets multiplied by 2. So if we are on the x-axis, meaning our initial distance from it is 0, then we do not move off of that x-axis. I encourage you to use your graphing calculator to check your work here. An alternate way to input y2 in this case would be to type y2 equals 2 times y1. In order to access y1, you would press the vars button and then select the y-vars menu before choosing function and function y1. In exploration number 2, we revisit the same graph of f of x equals the square root of x plus 4 minus 1. This time, rather than multiplying the y coordinates by 2, we'll multiply the x coordinates by 2. We can call this a horizontal stretch, as we'll see. Let's start by labeling the points on the graph. So if we double the x coordinate of the endpoint negative 4, negative 1, it would become -8, -1. Notice the y-coordinate has not changed and the x-coordinate has doubled. We'll now perform the same operation on all of the points. We'll note that when the x-coordinate is 0 and we double it, it remains 0. This means that a point on the y-axis is invariant. Now, if we're working with a function, meaning that each x value only generates at most one y value, we would never have more than one y-intercept, and so we'd only have one invariant point under this transformation. But if it were a relation, such as the sideways parabola that we may see later, then we could have multiple invariant points, all of which would be found on the y-axis, which is our stretch axis. Notice the point 5 and 2, which was right of the axis, moves more to the right, unlike the others which were the left and moved more to the left. Since the effect of this transformation is to double the distance of each point horizontally from the y-axis, which is to say we are doubling the x-coordinate, the mapping rule is represented as x, y becoming 2x, y. Again, all invariant points are on the y-axis as their x-coordinate is 0. We can type into our calculator the original function, y1 equals square root x plus 4 minus 1. If we want to see the transformed graph where we've stretched horizontally by 2, you'll notice that we insert a coefficient of 0.5 or 1/2 in front of the x. This is because horizontal stretches show up as their reciprocal in the equation. So when we see the parameter of b represented with 1/2, we say, oh, the stretch factor is the flip or reciprocal of that, which is 2 over 1. So stretch by 2. Now I'd like to add a point here that is jumping ahead a little bit, but hopefully will help later confusion if you jump back to this slide. Students often wonder when they put the 1/2 coefficient in front of the x if they should bracket the x plus 4. And the reason for this is typically when we discuss transformations or multiple transformations, we discuss stretches before translations. However, this function that we were working with, f of x, had already been transformed, which is to say, if we're thinking of all radical functions as being the base radical function with its endpoint at 0, 0, and then that they've been transformed from there, well, this one had been translated 4 to the left and 1 down. So given that it was pre-translated and was then stretched, we are dealing with an atypical order of the transformations, and as such, we would not be introducing brackets to the x plus 4. This might seem unclear or overwhelming for now, but just clarity again. If we have stretching before the translation, we would see brackets around the x plus 4, but here this was translated first. Exploration number 3 explores the graph of g of x equal to x squared minus 4. And then we compare this to two other graphs, one in which we bracket the x squared minus 4 and put a 2 in front, and one in which we put a 0.5 in front. I want to talk for 1 second as a brief aside about a helpful way to shift your thinking. I think when we first learn about placing points on a coordinate plane, we talk about x as being the left and right movement, and y as being the up and down movement. At this level of Math 30, it's much more productive to view x as an input value. And so at every possible input value, we generate an output value of y, or at most one output value of y. So here, if we think about this, that means that x is our input, and we're going to take whatever value it is, 1 or 2 or 17 or -4, and we're going to square it and subtract 4, and whatever it outputs becomes the height associated to that x value. Well, with that in mind, if you were to bracket that expression of x squared minus 4 and put a 2 in front of it, it should seem obvious that what's happening is for the same x value inputted, the result will be doubled and so the height will be doubled. So this is clearly a vertical stretch by a factor of 2. And when it's 0.5, we will see it as a vertical stretch by a factor of 1/2. So as we go through this, just know that you were able to anticipate that because the x squared minus 4 was the rule of the function that generated the output value. Here we go. Seeing the 2 in front indicates that all points will be twice as far from the x-axis. We will therefore take all the y-coordinates and double them. We'll notice that the points on the x-axis had heights of 0. When you double 0, it's still 0, so these points are invariant. Again, a vertical stretch has invariance on the x-axis. Now, when we looked at the original equation of g of x equals x squared minus 4, you might have recognized that as being in vertex form, where the vertex was 0 and negative 4. Notice, when we have y equals 2 times x squared minus 4, if we distribute the 2 out, we'd have 2x squared minus 8. So we can see from that the vertex would be found at 0 and negative 8, as our graph confirms. Trying this again with coefficient of 0.5, we should see a similar effect, but instead of doubling, halving the y-coordinates. Notice again that our vertex appeared at 0 and negative 2, which, had we distributed the 0.5, would have been observed in the vertex form. And notice again that the x-intercepts are the invariant points. Let's take a moment to remind ourselves that when dealing with vertical stretches, the coefficient that we see is in fact the stretch factor. So when we saw a 2, we vertically stretched by 2, and we saw 0.5, we were vertically stretching by 0.5. As I say vertically stretching, I should always be saying stretching about the x-axis, but just to make it easier to follow. In exploration number 4, we revisit f of x equals x squared minus 4, the parabola shown on the right. This time, rather than introducing a coefficient of 2 or 0.5 in front of the entire right side of the function, we will simply replace x with 2x or 0.5x. This is to say that the input value will be directly affected by a coefficient of 2 or 0.5. And as mentioned in an earlier slide, though an a value, which is a vertical stretch factor, appears in front and has a direct effect, which means if it is 2, then it doubles, a b value, which is the coefficient that goes in front of the x, or the input value, has a reciprocal effect. So here, where we see the 2 in front of the x, we're expecting a horizontal stretch by 1/2. And where we see the 0.5, we're expecting a horizontal stretch by 1 over 0.5, which is equivalent to 2. Let's have a look. As we're intending to double all of our x values, as we're intending to multiply all of our x values by 0.5 to half them, we note that our vertex has an x value of 0. Since we multiply that by 1/2 and still obtain 0, this is an invariant point. The points of -1 and +1 will multiply to give -1/2 and +1/2. Notice their y values don't change. Now you may note that this graph could be described as looking thinner, more narrow, which is the horizontal stretch by 0.5, or in some ways could be seen to be climbing more quickly. In fact, if we expanded the y equals 2x squared minus 4, we would get y equals 4x squared minus 4 if we multiply 2x by itself. This is important because it means that we can kind of describe a horizontal stretch and a vertical stretch equivalently, except that they are different. What we notice is if this were in fact a vertical stretch, our invariant points would be the x-intercepts and not the y-intercept. So when starting from the graph, looking for your invariant points can indicate what the stretch axis was. Here, because the vertex on the y-axis didn't move, it must have been a horizontal stretch. As we now replace the x with a 0.5x, or introduce a coefficient of 1/2 in front of the x, we'll see a horizontal stretch by 2. We're going to double all the x coordinates for each point on the original curve, and again, because the vertex has an x coordinate of 0, it will be invariant. So, from all of this, we deduce that a coefficient of b generates a reciprocal horizontal stretch. So when we see a 2, the horizontal stretch factor is 1/2, and when we see 1/2, the horizontal stretch factor is 2. Horizontal stretches are, in this course, always relative to the y-axis. Most of the key information from this slide has already been discussed. However, I would like to highlight 3 important points again. First, when dealing with a vertical stretch, the parameter of a will appear as a coefficient in front of the function. This value is the vertical stretch factor, which is to say, if we see the number 3, the vertical stretch factor is 3. When dealing with reflections, we'll recall that a negative sign will cause a reflection, but will not be considered part of the vertical stretch factor. So a value of -3 would still be a vertical stretch factor of 3, and then the negative sign corresponds to the reflection. The mapping notation shows xy becoming x and ay. Again, because each y-coordinate is multiplied by the a value. Because the x-intercepts have a height of 0, they are invariant points, as multiplying 0 by a has no effect. The last thing I would highlight is when we are working with what I will call a pre-transformed function, which is to say one that has already been translated, and we are then stretching it. Notice here that the 2 in front of the bracketed square root of x plus 4 minus 1, it distributes not only to the square root, but also to that minus 1, doubling it to be a -2. This makes sense when we look at the graph because we've seen the endpoint shift from -4, -1 to -4, -2, but is worth reiterating. A reminder, the parameter of b, which is the coefficient to x or the input value, is responsible for the horizontal stretching of a function. However, the horizontal stretch, which is about the y-axis, is by a factor of 1 over b, not b, which is to say, if we see 4x, then the horizontal stretch factor is 1 over 4, or a quarter. And if we see 0.5, then the horizontal stretch is 1 over 0.5, which is equivalent to 2. As such, the mapping notation shows xy becoming 1 over b times x and y. Because we're stretching relative to the y-axis, the y-intercept will be invariant. I would also like to highlight, with particular respect to the radical function written here, that when the coefficient under the radical sign is factored out of the binomial, so in the second version where we see 1/2 times a bracketed x plus 8, it is in that factored form that we should be able to identify the vertex coordinates of the radical function. And by vertex, I mean its endpoints. So the endpoint of the transformed function is -8 and -1, as we see in the equation. As we look again at the vertical and horizontal stretches generated by A and B values, students are often frustrated by the fact that A and B are treated differently. Well, we can say that they're treated differently because A is affecting the variable on the other side of the equation, whereas B is affecting the variable on the same side of the equation, because A affects Y and B affects X. But there is a way to look at this so that they are both treated the same. If we consider the transformations in terms of replacements, well, we could say that we're replacing, for example, x with 1/3 x and y with 1/4 y. In our first step then, instead of seeing y equals f of x, we would see 1/4 y equals f of 1/3 of x. Because we seek to isolate y, we would multiply both sides by 4, and in doing so, we would now see the a value of 4. Well, what that means is, in both cases, the replacement of x with 1/3 x and the replacement of y with 1/4 y, the effect was actually reciprocal. The replacement with 1/3 x was causing a horizontal stretch factor by 3, and the replacement with 1/4 y was causing a vertical stretch factor of 4. But again, because we isolate y and put that value to the other side, it actually appears in its direct form. So one more time, with A, what you see is what you get. And with B, the stretch factor is the reciprocal. In class example 1.31, we explore stretches on a piecewise function. We are given the graph of y equals f of x and asked to construct a mapping rule in order to sketch the graph of g of x equal to 1/2 f of x. We note that the 1/2 is out in front of the f and is not with the x directly. This means it is the a parameter value and not the b parameter value, and as such is a vertical stretch factor. Remember also that though a b value requires us to determine the reciprocal value, an a value does not. So the 1/2 will in fact be the vertical stretch factor. As such, our mapping rule will be that xy becomes x and 1/2 y. We could also write 0.5 if you prefer. The effect of this is that each point on the graph will have its y coordinate multiplied by 1/2, or divided by 2. And so we will see all the points above the axis, the x-axis, lower a little bit, and those below will raise a little bit, and the x-intercepts will remain the same. In this question, we're asked to determine the location of any invariant points. We're going to simply say on the x-axis. If the question asks us for the coordinates of the invariant points, we would have to use some of our Math 10 skills. For example, if we looked at the line segment joining -1 and 4 to 2 and -6, we could determine that it had a slope of -10/3. And with those points, we could then put that into y equals mx plus b form or slope point form, and from there could calculate the x-intercept. Similarly, for the line segment joining 2 and -6 to 6 and 2, we could determine the slope and using a point generate an equation and then find its x-intercept. However, that goes beyond what we're talking about here. Now, when asked to compare the domain and range of f of x and g of x, it's important to note that the only transformation applied was a vertical stretch. This means no horizontal transformation happened, and therefore the domain will be unchanged. We see that the leftmost point of f of x, which is the blue graph, the black graph with the blue points, the leftmost point had an x-coordinate of -5, and the rightmost point had an x-coordinate of 6. Therefore, its graph has a domain of -5 to 6, and g of x will have the same domain. Its range, however, does not look at the end points, but rather the highest and lowest point. So our highest point on the graph has a height of 4, and our lowest point has a height of -6. Notice in both the domain and range, we've used brackets that are rectangular and turned inward because we are including those values. An outward turned bracket in interval notation would only occur where we had a hollow point. So again, because the domain is unchanged, it will remain as -5 and 6. Our range, however, underwent a vertical stretch by a factor of 1/2. So even without looking at the transform graph, I know that if I half the -6 and half the 4, which were the y minimum and y maximum value in our range, I will find the new range of -3 to 2. We could also do this by looking at the graph and seeing that the lowest point occurs at a height of -3 and the highest point at a height of +2. Though we work with a values and b values differently, class example 1.32 is rather similar to class example 1.31. I encourage you to pause the video and give it a try before you advance. Here, we're given another piecewise function, y equals f of x, and we're asked to construct a mapping rule to sketch the graph of g of x equals f of 3x. We need to remember that a b value, which is to say a coordinate in front of x, has a reciprocal effect. So when we see 3, the effect is that we have a horizontal stretch by a factor of 1/3 relative to the y-axis. So let's label the points on our graph and multiply each x coordinate by 1/3. We'll note this time that our invariant point is located on the y-axis. Now, in this graph, our invariant point actually passed through the origin, so it is simultaneously a y-intercept and an x-intercept. But you will note that there are other x-intercepts for this graph, and they have changed position. So it is in fact the y-axis that is our stretch axis, and that's where we find our invariant points. In order to discuss the domain and the range, let's first find the domain and range of the original graph. We had a leftmost point with an x coordinate of -9 and a rightmost point with an x coordinate of 12. The lowest point on the graph was in fact that end point on the right with a height of -6, and the highest point had a height of 3. Now, can you figure out what's going to happen here? We have a horizontal stretch by 1/3. Note we've had no vertical transformations, so we expect our range to remain unchanged. But for our domain, we're going to take our minimum x value of -9 and our maximum x value of +12 and multiply both by 1/3. This gives us -3 and +4. As a quick check, you can note that the original graph, going from -9 to +12 horizontally, had a width of 21 units. Now, going from -3 to 4, it has a width of only 7 units. That is 1/3 as wide. Now that we've seen a few questions where we apply stretches to a graph, let's look at one where we're just given the equation. In class example 1.33, we'll work with an absolute value function that is both reflected and stretched. So the function f of x, which is equal to the absolute value of x minus 5 plus 8, has a range of y greater than or equal to 8. This would make sense if we picture an absolute value function, typically with a vertex on 0, 0. The x minus 5 shows that we've shifted 5 to the right, having no effect on the range, but then moving 8 up means that our range would be greater than or equal to 8 rather than 0. So to obtain a function g of x, we reflect the graph y equals f of x about the line y equals 0. The line y equals 0 is another name for the x-axis. So this is a vertical reflection. And then we apply a vertical stretch by a factor of 1/4. meaning each y coordinate is multiplied by 1/4. Note, when we talk about vertical stretch factors in a word problem, what it tells you is in fact the stretch factor. So even if this were talking about a horizontal stretch factor of 1/4, it would actually be a stretch factor of 1/4. We don't worry about the reciprocal until we go to work with the equation and having to write the coefficient there. So the first part asks us to determine an equation for y equals g of x in terms of f of x, and then in terms of x. What does it mean to write an equation in terms of f of x? It means that we simply represent the original function as f of x and represent the transformed function g of x as a transformed f of x, which is, say, we just write in the parameters that affect it. So here we had a reflection in the x-axis. That is a negative a value. And we had a vertical stretch by a factor of 1/4. That is an a value of 1/4. So our g of x equation would be negative 1/4 times f of x. If we then want to write that in terms of x, we would replace f of x with its original expression of absolute value x minus 5 plus 8. Notice that it is bracketed there. So those vertical lines are the absolute value brackets, and then we have rounded brackets around that. Using the distributive property, we will multiply that negative 1/4 to the absolute value brackets and also to the positive 8, generating a negative 2. A reminder, because it's been a while since you've worked with absolute value functions maybe, that the fact that there's an x minus 5 affected by an absolute value does not mean we'll change that to x plus 5. Right? It's only after that internal expression of x minus 5 is evaluated that we apply the absolute value function. Now, part B asks us to state the range of g of x. Well, remember our original range was y is greater than or equal to 8. So what happens if we reflect that over the x-axis? Well, if you can picture the original graph as being the blue one shown there, then the transform graph would be the green one, the one that is below the x-axis. Notice that the vertex of the original was at 5 and 8, and the new one is at 5 and negative 8. So instead of our range being above positive 8, we are below negative 8. It's important that you change both the direction of the inequality, but also that you change it from being positive 8 to negative 8. Now after that, we apply a vertical stretch of 1/4, which effectively shrinks our negative 8 to a negative 2. So this is what the original graph would look like compared to its transformed graph. Class example 1.34 asks us to apply a stretch to both the graph of a function and to its equation. Here we're given f of x equal to negative x minus 2 squared plus 9. So this is a quadratic function, or a parabola, given in vertex form. We know from that negative coefficient that this will be opening downward, and that its vertex will be at positive 2 and 9, as shown in the graph. So then it says the graph of g of x is obtained by vertically stretching the graph of f of x about the line y equals 0. Well, as a reminder, formally we would often simply say that it will be stretched about the line y equals 0 and will not include the word vertically. But we know it's vertical because the line y equals 0 is the x-axis. And when we stretch about the x-axis, that is always a vertical stretch. Next it says this will be by a factor of 3, so all the y coordinates will be multiplied by 3. And then there will be a reflection in the line y equals 0, again the x-axis. So when we see that vertical stretch, we know that when it says a factor of 3, that's telling us the a value, and because there's a reflection, it will be a negative a value, so negative 3. One thing that can be really helpful when you're graphing multiple transformations is to represent the transformations using a mapping rule. So here, because both of our transformations are vertical, they'll both reflect the y coordinate, so xy becomes x and negative 3y. This means if we wanted to transform our graph, we can simply take each point and multiply its y coordinate by negative 3. Let's try this. So for the vertex of 2 and 9, we will multiply the y coordinate of 9 by negative 3 to get negative 27. We're asked to repeat this same process and to indicate the new location of the x and y intercepts and other key points. Given that we're graphing a parabola, the vertex and the intercepts are basically all of the key points. If we had a more complicated polynomial function or a piecewise function, we might have some other local minima or maxima to indicate, but here the intercepts and the vertex would probably be sufficient. We'll note again that the x-intercepts, because they have heights of 0, will remain invariant under this transformation. So looking at a result, we now see a graph of a parabola opening upward with a vertex at 2 and negative 27. If we write the equation for g of x in terms of f of x, it would be g of x equals negative 3f of x. This is because there is a reflection and a stretch by a factor of 3. When we want to write this in terms of x, we would now replace f of x with its equivalent expression of negative x minus 2 squared plus 9. And as we distribute that negative 3 through, we see that it becomes positive 3 x minus 2 squared minus 27. And that makes sense given our corresponding graph, because our graph was opening upward, so a positive a value, and had its vertex at positive 2 and negative 27, which we now see explicitly in that vertex form. Again, the location of our invariant points will be on the x-axis. If we wanted to determine their exact coordinates, we could take that transformed equation in green, y equals at 3 times x minus 2 squared minus 27, and replace the y value with 0. We would then solve for x. This graph, we can clearly see the integer values of 5 and negative 1, so that's not really as necessary, but could be helpful in another case. A parabola will always have either a maximum value or a minimum value, and will then extend to either positive or negative infinity. So in our original graph, we went from negative infinity up to positive 9. As we can see in the graph of our green graph, we now have a minimum height of negative 27 going up to a maximum of infinity, which we never reach, hence the rounded brackets. Let's continue class example 1.34 with the same quadratic function, but this time, rather than having a vertical stretch and a reflection, we'll simply have a horizontal stretch. Now the question is going to say, given f of x equal to negative x minus 2 squared plus 9, that h of x is obtained by horizontally stretching the graph about the line x equals 0. I remind you that we don't need to say horizontal there, because once we've said about the line x equals 0, it is implied that it's a horizontal stretch. What's important here is, we're going to start by writing the mapping rule. And we're going to do that because we're working with the graph. We want to sketch the transformed graph. When we read in words that the horizontal stretch factor is 3, a lot of students question, should I be writing the reciprocal in the mapping rule? And the answer is no. When we write a mapping rule, we are representing the effect on each point. And a horizontal stretch by a factor of 3 has as its effect to take each point 3 times as far away from the y-axis. So it really is multiplying the x-coordinate by 3. The only time we see the reciprocal relationship is between the stretch factor and or the mapping rule and the equation. So later in the next step, when we write the equation, that's when we'll see the reciprocal. We'll label each point here, and now let's go ahead and multiply the x-coordinates by 3 to see the transformed graph. I am a huge fan of using the mapping rule to graph transformed graphs because it helps us avoid common errors. And I'll call them oopsies because you probably didn't even mean to do this, but Often when students are asked to stretch something horizontally and they're working on the graph, rather than doing it about the axis, they do it about the vertex, which is to say they keep the 2, 9 at the point 2, 9, and then they move the points below that further out. But all points are on kind of a canvas here, and the canvas is being stretched, right? So the every single point, even the vertex, is moving 3 times as far away from that y-axis. So the point 2 and 9 becomes 6 and 9. Notice our y-intercept being on the y-axis did not move because 0 times 3 is still 0. That is our invariant point of this graph. So to write the equation for h of x in terms of f of x, we need now to write the b value. Well, the b value is the reciprocal of the horizontal stretch factor. Otherwise said, the horizontal stretch factor is the reciprocal of the b value. So since we've stretched by a factor of 3, the b value must be 1/3. To write our equation in terms of x then, we would take the original equation, and in every instance of x, so in this case in the bracket where it's at x minus 2, we would replace that x with 1/3 x. We can check this in our graphing calculator and confirm that it gives us the properly transformed graph. Simplifying this, or rather factoring it to represent it differently, is a little bit tricky because we have to factor the 1/3 out of the binomial of 1/3 x minus 2, and when we divide that -2 by 1/3, it becomes -6. Notice that the square, which is to say that the exponent of 2, is on a bracket outside of both the x minus 6 and the 1/3, but not the negative coefficient. So now we can square the 1/3 without squaring the negative sign to achieve a final state of y equals -1/9 x minus 6 squared plus 9. As mentioned earlier, our invariant point was at 0 and 5. In class example 1.35, we're given the graph of an absolute value function defined as f of x equals the absolute value of 2x plus 6 minus 12. We're then asked to sketch the graph of a new function g of x, which is defined as f of 3x. The big idea of this question, of course, is identifying which parameter is represented by the 3 and what the effect will be on the graph. We've talked earlier about how a coefficient appearing in front of the f would be an a value and a coefficient with the x would be a b value. So this is a b value. We know that the horizontal stretch factor is the reciprocal of that b value. So here we are expecting a horizontal stretch by a factor of 1/3. We represent this in the mapping rule by writing that xy becomes 1/3 of x and y, showing that each x coordinate is multiplied by 1/3. Let's go ahead and label the points on the graph and apply this transformation. When sketching a transformed graph, or when verifying the sketch of a transformed graph, I suggest you always start by looking at the invariant points. Here, because we've stretched horizontally, we should see invariant points on the y-axis. And sure enough, the intercept at 0 and -5 is our only invariant point. All other points should have shifted closer to the y-axis. Next, we're asked to determine an equation for g of x in terms of x. This means we'll have to make a replacement into the equation absolute value 2x plus 6 minus 12. Now, what do we use? Do we use the 3x or do we use the 1/3 x? Well, remember that the mapping rule tells us the truth about what really happened. So if we describe this in words, we'd say a horizontal stretch factor of 1/3. And a replacement should always be the opposite of that. So in this case, the reciprocal. So here, we will replace the instance of x with 3x. Now we can simplify this. The first step is probably the most obvious simplification and would generally be enough. However, we could take this a little bit further by factoring out the 6. And because that 6 is positive, the absolute value of that factor will remain 6. So we can write it out front like this. This added step is not necessary, but is equivalent. As always, you're encouraged to verify your answer using your graphing calculator. In class example 1.36, we're asked to use our knowledge of horizontal and vertical stretches to determine which stretch has occurred in each case and by what factor. We'll then use that information to determine the mapping rule and the equation. Now, in our first example on the left, part A, we see a dark blue or maybe black graph, y equals f of x, and its transformed version in green, y equals g of x. We've already been told that the transformation that occurred was a stretch, so we just need to determine if it was horizontal or vertical. Well, in some cases, it's really obvious, and you might be able to tell here because the graph kind of looks thinner. But what we really want to focus on are the invariant points. Did the x-intercepts change? Did the y-intercepts change? And here we see that the one pair of corresponding points that have not changed, which is really an invariant point, is the y-intercept. When I say corresponding points, if we look at, for example, in one of the end points, we can see that on the transform graph, it's not in the same place as it was. And similarly, when we look at the x-intercepts, we can see that they correspond to a different position. However, the y-intercept is the same on both the original and the transform graph. So now that we know that it is a horizontal stretch, we want to know by how much. To determine the stretch factor, we will compare two corresponding points. In this case, it won't be helpful to use the invariant points because they haven't moved. So let's look at the end point. The farthest right point, or rightmost point, on the graph of f of x is 8 units from the y-axis, horizontally, of course. And the corresponding point on g of x is 4 units from the y-axis. Now be careful, we're not talking about translation here, so we don't want to say they're 4 units apart. That won't be helpful. What we want to determine is what the 8 was multiplied to change it to a 4. So 8 multiplied by some horizontal stretch factor became 4. A quick division of both sides by 8, and we see that the stretch factor is 1/2. Now remember, the stretch factor shows up as it is in the mapping rule, which is to say, if the stretch factor is 1/2, we'll see the coefficient of 1/2. So here our mapping rule is that xy becomes 1/2 x and y. However, because this is a horizontal stretch, it corresponds to the b parameter, so the coefficient in front of x. And we remember that there is a reciprocal relationship between the stretch factor and the b value. So here, f of 2x would be the parameter that would lead to the stretch of 1/2. Having worked through example A, you can probably handle B on your own. Why don't you give it a try? Can you determine the mapping rule and the equation for g of x? Well, as stated before, the first thing to do is determine whether this is a horizontal or vertical stretch. We note right away that this graph has 3 invariant points, this transformation has 3 invariant points, and all of them are located on the x-axis. This means the graph has been stretched vertically. Now we need to find any 2 corresponding points to determine the vertical stretch factor. Well, let's use the y-intercepts, which are clearly marked on this one. On f of x, and it is important to determine which one was the original. On f of x, our intercept was 6 units above the x-axis, while on g of x, it is 9 units above the x-axis. Again, we don't want to talk about it going up 3, because that treats it as translation. We want to know by what factor do you multiply 6 to generate a 9. So 6 times the vertical stretch factor becomes 9. We can isolate the vertical stretch factor to determine that it is 3 over 2. Now you notice here, I didn't use the letter A, even though I could have. This is mostly because we aren't certain if A is positive or negative. And in the case of the horizontal stretch factor, it corresponds to 1 over B, and writing 1 over B can lead to student confusion. So we just used VSF here for vertical stretch factor and hope that that's satisfactory. Well, because that vertical stretch factor is in fact the A value, we will write the mapping rule of xy becoming x and 3/2 y. You could also write 1.5 there, because what you see with the vertical stretch factor is what you get as your A value. Similarly, when we write the equation, we talked earlier about how replacements would make this show up as the reciprocal of 2/3, but typically when we write the equation, the A value appears on the right side of the equation in front of f and as its true horizontal stretch factor value. So here, g of x to be equal to 3/2 f of x. Now that we're feeling more comfortable identifying whether a stretch is vertical or horizontal, let's look at some equations that are perhaps problematic for students. We'll start with example A, where we see a blue parabola, f of x, which is defined by 2 times x minus 3 squared minus 8. We know that the 3 and the negative 8 correspond to the vertex, and we know that the 2 makes the graph rise more quickly. That 2 will have an effect on our equation in terms of x, but will not appear in the equation in terms of f of x, as we'll see later. For now, let's determine whether this is horizontal or vertical, and by what factor. So because our invariant points are on the x-axis, we can determine that this has been a vertical stretch. By comparing the vertices, the first at negative 8 and the second at negative 1, we can see that the negative 8 has been multiplied by 1/8 to become negative 1. We know that our mapping rule will show that A value as a coefficient of y. We also know that our equation in terms of f of x will show that 1/8 as the A value in front of f of x. However, when we go to write the equation in terms of x, it will be important that we put the 1/8 in front of a bracketed, in front of the bracketed original expression. This is to say that the 2 times x minus 3 squared minus 8 will all be affected by the 1/8. If we look just inside those rectangular brackets, there are 2 terms. There's the 2 times x minus 3 squared term, and then there's the negative 8. So many students will multiply the 1/8 by the 2 to get 1/4. But it is critically important that you also distribute the 1/8 to the negative 8 to get the negative 1. Let's go back a second. We knew that the blue parabola had a vertex at 3 and negative 8 before we even graphed it. If you were to forget to multiply the 1/8 to the negative 8, then in your g of x equation, it would say 1/4 x minus 3 squared minus 8. But that's not possible because we've already seen that the vertex moved to 3 and negative 1. And so that's why in this new equation we see the 3 and the negative 1. Anytime you're asked to find a y-intercept, you can always replace x with 0. Here, we could replace x with 0 in the transformed version, the g of x form, and we would get 1/4 times 0 minus 3 squared minus 1. And after some work, we would arrive at 5/4. Alternatively, because the original graph, the blue parabola, had its y-intercept at a height of 10, we can simply multiply that by 1/8 to get 10/8, which reduces to 5/4. Now we'll look at part B, where we deal with a radical function. Students are generally quite comfortable with the parabola because we worked on it so much in Math 20. Sometimes we're less comfortable with the radical function, but it's almost easier because you have a clearly defined endpoint, which you know corresponds to the endpoint on the other graph. So here we're given the equation of f of x as being the square root of 32x plus 64 minus 4. I'd like to point out that at this step already, if you factor that 32 out of the binomial under the radical, so that it said square root of 32 bracket x plus 2, that 2, which would correspond to -2, and -4 would represent the vertex or endpoint of the blue graph. So here, we got to first determine whether this is vertical or horizontal and by what factor. Well, comparing the blue graph to the green graph, we see only one point remains unchanged. The y-intercept at a height of 4 is invariant, as it lies on both graphs. To determine what our stretch factor is, now that we know that it's horizontal, we'll say on the f graph, we had a vertex at -2, or 2 units away from the y-axis. And on the transformed graph, we are now 8 units from the y-axis. Don't talk about moving 6 left. We want to know by what did we multiply. For a 2 to become an 8, we need to multiply by 4. Well, we're feeling pretty good about ourselves having determined the horizontal stretch factor, but be careful, because though it shows up as a 4 in the mapping rule, it does not for the equation in terms of f of x. Remember, a horizontal stretch factor is the reciprocal of the b value. So if your stretch factor is 4, your b value must be 1/4. And that's what we write in g of x equals f of 1/4 x, is the reciprocal of the stretch factor. Now, once we put this into the actual equation in terms of x, remember, we don't have a bracket affecting that 64. We are simply replacing x with 1/4 x. A replacement is always the opposite of the actual effect on the graph. So here, the effect was a stretch by 4, the replacement is by 1/4 x. All that's left to do now is to simplify. Now, the square root of 8x plus 64 minus 4 would be the most simplified version, but a better version would be if we factor out the 8. Why better, you say? Because here we see the h value, or the 8, which shows us that we've been shifted 8 units left off the y-axis and 4 down. But that refers to the original base radical function. So it's a little bit tricky here. I'm not saying that the blue graph shifted 8 to the left. I'm saying if we treated the green graph as being independent from the blue graph, but rather being a transformed version of a base radical function of y equals square root of x, then the 8 out front the bracket would show a stretch by 1/8. The 8 in the bracket shows the translation to the left, and the -4 shows the translation 4 units down. That's a lot of information to put together, but I believe that you understand now the difference between a horizontal and a vertical stretch and how to determine the stretch factor. Keeping the stretch factor versus a value and stretch factor versus b value, or 1 over b value straight, is another thing, but with time and practice, you'll get it. Having found the equation of the transformed function, it's always a good idea to check this graphically. Here, if we put the f of x function in our calculator and our newly determined g of x function in the calculator, we should see an image that looks the same as we have on our screen. Now, notice we were given a graph that went from negative 10 to 10 horizontally, but negative 5 to 16 vertically. You'll probably want to shift your window to these same values so that you really do see the same image. Finally, we're asked to determine the x-intercept of f of x. Now, f of x was the equation we were given, so we don't have to work with our transform function here. Let's go ahead and take that f of x equals square root of 32x plus 64 minus 4 and replace y with 0. We replace y with 0 because an x-intercept always lies on the x-axis where the height is 0. In this first algebraic step, I've actually added 4 to each side, but then just for ease of writing it, I've swapped the sides so that the square root is on the left side. Think back to Math 20. In order to solve a radical equation, we want to square both sides once the root is isolated. So here we square, and on the left that simply cancels out the square root sign over the 32x plus 64. On the right side, the 4 squares to 16. After a little bit of subtraction and some division, we find that x corresponds to 3 halves. This means that our x-intercept is negative 3 halves and 0, or negative 1.5 and 0. Now, a lot of students will get worried when they get a negative answer for something that had been under the square root sign. But don't worry, because 32 times negative 3 halves, or negative 1.5 plus 64, gives a positive value. And it doesn't matter that x was negative, it only matters if it generates a negative radicand, which is to say if it makes the part under the root sign turn negative. As an alternate method, because we were given the x-intercept of g of x on the graph as being negative 6 and 0, and because we know that f of x was stretched by a factor of 4 to generate g of x, going back the other way we could say, well, f of x is 1/4 of g of x horizontally. So negative 6 times 1/4 generates negative 1.5. That said, that strategy is much less often going to be as helpful as recognizing that an x-intercept is when you set y equal to 0.